Hello and welcome to this section of the chemistry tutor. In this section we're going to talk about what we call percent composition and empirical formulas of compounds. So up until this point we've learned some very important core topics in the last few lessons. In this section we're going to again look at chemical compounds and what comprise and make up a chemical compound and talk about calculating what the percentage is of the different elements in those compounds by mass. That's what we say percent composition, so percent composition by mass basically. And then we're going to learn how to do those calculations, and we're going to talk a great deal about empirical formulas, and you'll see how that's tied together. We'll review what an empirical formula is. We'll talk about how to find out how to calculate or write down the empirical formula and be given some data. It'll be tied into percent composition also in this section. And in the next section, after we get through these two topics, we'll be talking about writing our first chemical reactions. So that's sort of like what you think about when you start thinking about chemistry, chemical reactions. Well, we're building up our knowledge. So stick with me here, one step at a time. You'll understand everything before it's all over. All right, so the deal with this section here, percent composition. So you have a chemical compound, H2O, something that you understand, H2O. You know that means that you have 2 atoms of hydrogen for every 1 atom of oxygen. You know that, right? So what if I asked you, what is the percent composition of the hydrogen that's in that molecule? Well, you might be tempted to say, well, it's 2-to-1 ratio, so I'm just going to use that 2-to-1 ratio to calculate a percentage. But see, when I say percent composition in chemistry, usually almost always I'm talking about what is the percent composition by mass. In other words, this water molecule, if you could put it on a balance, would have a certain mass. And the hydrogen inside of it would have a certain mass, and the oxygen would have a certain mass. If you add up the mass of the hydrogen and the oxygen, you're going to get the mass of the whole water molecule, right? So what's the percent? Is it 30% by mass of hydrogen? Is it 50% by mass of hydrogen? What is it? Well, you see, hydrogen and oxygen have vastly different masses. So we have to use the chemical formula in addition to the knowledge of how much these different elements have, what the different masses are, to find out what the percentage is of that hydrogen or whatever it is in that compound. And this is really important actually because, we're doing this from the point of view of learning chemistry, but let's pretend that you discover some element, and never been seen before, don't even know what the heck it is, right? One of the very first things you're going to do is put that thing in a machine in a laboratory to measure the percent masses of the different elements in it. So it'll go in there, it'll do an analysis, and you won't know what the chemical formula is, but you'll know that it's maybe 38% carbon, 42% silicon, and so on. And from that you can go on and investigate the structure of the compound that you have. So if you're sending a probe to Venus or to Mars, that's very practically what we're doing. So try not to look at this as this boring thing we're calculating. I mean, this is what you would do if you were going to explore another planet and go dig a rock up and figure out what percentage it's made up of the elements there. The easiest way to teach this is just to do examples. So I'm not even going to go into any theory. We're just going to dive right into it. So what if we want to find the percent mass composition of every element in the following formula here? So barium, silicon, oxide. So barium, 1 atom of barium, 1 atom of silicon, 3 atoms of oxygen. And what we want to know is, what is the percent composition by mass? When we say percent composition, we're talking about by mass of barium in this compound. What is the percent composition of silicon in this compound? What's the percent composition of oxygen in this compound? Now, like I said before, there's really 2 variables here. Obviously, there's more atoms of oxygen than silicon. There's more atoms of oxygen than barium. So that's going to factor into the answers that we get, right? But also, each of these elements have totally different masses, right? So silicon is going to have a totally different mass of oxygen. So even though there's 3 more oxygen atoms, it doesn't really tell you the percent composition by mass, because everything else in the guy they may be super heavy. These other guys might be super heavy, much heavier than oxygen. So it's totally going to skew the percent composition by mass another direction. So we need to use 2 things to calculate percent composition by mass. We need obviously how many atoms are in the molecule, and we need to know what their masses are. And we've already talked about, from our discussion of moles, the way you get the masses of these elements is from the periodic table, grams per mole. That's basically the atomic mass that we read off of it. We can read it in terms of grams per mole. So the very first thing that we need to do before we there's a very bulletproof way to do this. So the first thing we do, let's find the mass of barium silicon oxide. And what I mean by let's find the mass of it, I mean let's find the mass of the whole thing. Because don't forget, what is the percent of anything? What's the percent of flipping a coin? The percent of getting heads? Well, you know it's 50%. You know that, right? But how do you calculate it? It's part over whole. So in that case of the coins, you have two different sides, right? And you have one head. So it's part over whole. So 1 over 2, 1/2, which is 0.5, which is 50%. So in general, the way you calculate a percentage of any kind is it's part over whole, and you multiply by 100 because we're making it into a percentage. So this part over whole business, that's going to give you a decimal multiplied by 100. So what we're going to basically do here is first find the mass of the entire compound. That's going to be our whole. That's going to be the mass of the whole enchilada on the bottom. Then we're going to go back and find the masses of each guy individually, and we're going to do part over whole for every one of them, and that's going to calculate our percentage. So the mass of barium silicon oxide. When you look in the periodic table, then what you're going to see for barium is, for an atomic mass, you're going to see 137.33. Don't ever forget what units you have here. This is grams per mole. So if we shovel out a mole of this stuff, it's going to be 137.33 grams. This is the barium. Plus, the silicon, if you read it off the periodic table, is 28.09 grams per mole. Plus, the oxygen. Now the oxygen is a little different because we have 3 of these guys. So to find the total mass of this oxygen here, it's going to be 3 times the mass that we read off the periodic table, which is 15.99 grams per mole. Okay, so what we have here, just to make it absolutely clear, this is the mass of that barium, this is the mass of that silicon, and this number in here is the mass of this oxygen. Now we multiply it by 3 just because we have 3 oxygens. So when you find the molar mass of something, you just need to use these subscripts and multiply by whatever you read off the periodic table. Is really the bottom line. So when you do this plus this, let's go ahead and write it explicitly one more time. Let's write the 137.33. Let's plus 28.09 plus, I'm just writing it again because I want to do this multiplication. 3 times 15.99, let's go ahead and write that as 47.97. All right, so this goes with the barium, this goes with the silicon, this goes with the oxygen. So the total amount of oxygen in there has this many grams per mole. All right, so the answer that we get here, which is not the answer to our problem, it's an intermediate step, is, what we're saying is that barium silicon oxide has a mass equal to 213.39 grams per mole. All right, so this is important. This is not the answer, though. This is the mass of the entire compound. The barium plus the silicon plus the 3 oxygen atoms means that if I shovel out 1 mole of this guy, it's going to actually have a mass of 213.39. So this is like the whole that's going to go in the denominator here for the percentage. And we're going to find the percent mass of each thing, but we have to be dividing by the total mass of the whole compound. So I kind of want to circle this a little bit because it's important, but it is not the answer. This is just an intermediate step to find the answer. Okay? So let's go ahead and calculate the answer. The percent for barium, right, which is the first element here, is going to equal the mass of barium, only the mass of the barium in this compound, divided by the total mass of the compound, then you multiply by 100. What is the mass of the barium by itself? Well, there's only 1 barium atom here, so we already figured this out. The mass of 1 barium atom is 137.33 grams per mole. Let's divide it by the mass of the whole compound, 213.39. Again, grams per mole, grams per mole. And we're going to multiply whatever we get in our calculator by 100 because this guy is just going to give us a decimal. It's going to give us a decimal between 0 and 1 somewhere. We're going to take that decimal and multiply by 100. That's what gives us a percentage. So what we're going to get, just to make it clear, is 64.36% barium. And this is one of the answers that we're seeking. So if you stuck this guy in a machine, you didn't have any idea what it was, and it just measured the percent of barium that's present, it would measure 64.36% barium. So let's go to the next guy, the percentage of silicon. Again, it's how much silicon is in this compound in terms of grams per mole divided by the whole compound mass. The mass of silicon we already wrote down is 28.09. 28.09 over the total mass of the compound, 213.39 times 100. Because again, this is just giving you a decimal, then you multiply by 100, that converts the thing to a percentage. And so when we do this, we'll get 13.16% silicon. So if we stuck this guy in our magic machine, which is a mass spectrometer, by the way, is what it's called, then it would measure 13.16% silicon. Let's go and do the final thing for oxygen. So the percent oxygen. Now, don't forget what we're doing. We're trying to on the top, we're putting in how much oxygen is in the compound. On the bottom, we're putting the total mass of the compound. So when we go figure out how much mass of oxygen is in the compound, we need to talk about how much total mass is, including the fact that there are 3 atoms here. So that's why we did the math this way. 3 times this mass that we get from the oxygen on the periodic table gives us 47.97. That's why I wrote it out second time, so you would have this number, 47.97. This is the amount in grams per mole of oxygen in this molecule. So then we go and divide it by 213.39, because that's the mass of the whole thing. So it's part over whole every time. We do this division, we get a decimal, multiply by 100, we're going to get 22.48% oxygen. So this is what we have. Now, a couple of things to make sure you understand. This is a bulletproof way. This is the way you're going to do all of these things. When you find percent mass composition, you need to find the mass of the whole compound. You do that by looking at the periodic table and using the little subscripts to multiply out and get what the total mass is in grams per mole. Then when you want to find the percent of each element in there, you've got to go back through the formula and set up part over whole, part over whole, part over whole, each time using the mass of that particular element, including how many subscripts that we have, because that's going to be the total amount of oxygen in this guy in grams per mole. This is the total amount of silicon in grams per mole. This is the total amount of barium in grams per mole. And when you do that, you should get percentages that, since we're talking about percentages, these guys should always add up to 100%. If we know the element only has, or the molecule only has 3 atoms, or 3 different types of atoms, then when we take the percent of barium plus the percent of silicon plus the percent of oxygen, we should get 100%, because we should end up accounting for everything in that molecule. If we don't get stuff that adds to 100%, then we made a mistake somewhere, right? It's like on a given weather day, right? There's a 40% chance of rain. That means that there's a 60% chance of no rain. That's what that means. And you add them together, it's got to equal 100%, because no matter what, on Wednesday, it's going to either rain or it's not. So you have to add those 2 percentages together. They should add to 100%. Same thing here. And if you put these in your calculator, you'll see that to within a tiny decimal place, they do add to 100. Right? So part over whole every time. Now let's go and do another one to kind of make sure you understand and go from there. So let's say we want to find the percent mass, or the mass percentage of every element in the following compound. This is magnesium, HCO3, 2. So we have a large compound here. We've got this polyatomic ion, HCO3, but we have 2 of them. So we have this on the outside of the parentheses, and we have magnesium out in front. Now before we do that problem, I want to draw your attention to one thing that I kind of hinted to before, but I want to make sure you understand. When you just look at this formula, like forget about the math we did, and you'll just look at this, and I ask you, hey, what do you think who's going to have the biggest percent composition in here? Most people would pick the oxygen, because there's 3 oxygen atoms here. There's only 1 atom of silicon and 1 atom of barium, so obviously this is going to have the most percentage. But when you look down, actually oxygen is not the highest percentage. Barium is the highest percentage. And that kind of comes back to what I was telling you at the beginning. The reason is because even though there are 3 oxygen atoms here, yeah, there are more atoms there, barium has a hugely more mass, a much, much larger mass per atom than the oxygen. So it kind of dwarfs it, I guess is what I'm trying to say. And that just falls out of the math. I just wanted to point that out to you. So don't ever look at a problem and think that you can just guess or kind of have an intuition. I mean, you can't really do that unless you do the math. Now, the way to tackle this, don't be scared off because it's a more complicated guy. You have to do it the same way. First thing we're going to do is find the mass of magnesium HCO3 2. That's the first thing we're going to do. So, the magnesium. Let's do this in red. The magnesium here. If you look in the periodic table, we have one atom of magnesium. On the periodic table, you'll see 24.31 grams per mole. Okay, that's for the magnesium. The reason that we don't multiply it by anything is because we only have one atom of it. Now, to find the mass of the whole thing, we need to add to it. Now look what we have. We have a hydrogen on the inside. There's a 1 just next to the hydrogen, but don't forget that you have a subscript 2 outside of the whole thing. So even though there's a 1 here, really you have 2 atoms of hydrogen running around here because you have the entire polyatomic ion is duplicated 2 times. So basically you have 1 times the 2, so you have 2 hydrogens. So you need to put a 2 times the mass of hydrogen, which is 1.008 grams per mole. All right, so this is for hydrogen. Then you need to add to that how many atoms of carbon. Again, there's a 1 here, but you have 2 entire polyatomic ions, so it's 2 atoms of carbon. Carbon is 12.001 grams per mole. And then finally, for oxygen, yeah, you have 3 oxygens on the inside, but you have this entire thing duplicated twice. So the way you figure it out is 3 times 2 really means that for every molecule here, I have 6 oxygen atoms. So I have 6 times 15.99 grams per mole. So just to make sure we're on the same page, this is for the magnesium. This guy is for the hydrogen. This guy is for the carbon, and this guy is for the oxygen. And we just use the subscripts to go off and figure all that stuff out. Now let's go ahead and do a little simplification. So this guy stays the same, it's 24.31 plus 2 times this guy is going to give me 2.016. So the magnesium goes with this number, the hydrogen goes with this number. This is grams per mole, right? Plus 2 times the 12.001, actually it's 12.011, like this. Okay, so we do 2 times this, we're going to get 24.022, so the carbon goes with this, plus 6 times the 15.99 is going to give me 95.94. So the oxygen goes with that. So all we did was do the multiplication that we laid out in the step above. So this means that in this molecule here, there's 24.31 grams per mole of magnesium, and so on. You can do that for every guy right there. If you were to measure out how many moles, or if you were to look at 2.06 or 016 grams of this guy, it would be 1 mole of that hydrogen that's comprised inside of there. So then what we have to do next is add everything up. So what we'll find out is that what we have is magnesium HCO3 2 is equal to, we add all of these numbers together, we're going to get 146.29 grams per mole. So individually, we found everything individually, but when we add everything together, what we find, and I'll circle it, but it's not the final answer here, that if we shovel out 146.29 grams of this stuff, that's going to be 1 mole. If we, that's how many grams in every single mole. So this is the whole that we talked about before. This is how many grams in the whole entire thing. Now, to find the percent by mass of each thing individually, we have to go back through and do the calculation. So the percent of magnesium is equal to part over whole. So in one, molecule here, so to speak, or one little unit, you look at this guy and say, well, I have 24.31 grams per mole of magnesium. The whole entire thing has a mass of 146.29 grams per mole of the whole compound. So we multiply by 100. Part over whole times 100. So when we do this, we get 16.62% of magnesium. So that's one of the answers. Now let's go back and look at hydrogen, the next guy here. So the percent composition by mass of the hydrogen in here is going to be part over whole. So we look back at our calculations. This was the hydrogen. We did the multiplication. This is how many grams per mole of hydrogen we have. So we have 2.016 over the whole entire molecule, 146.29 times 100, right? And then when you do this division, you're going to get a small decimal times 100. You're going to get a whopping 1.38% of hydrogen that exists in this molecule by mass. Next, let's go to the next atom, carbon. And what you'll get there, again, part over whole. We look back at our calculations. This is how much carbon we had in a single molecule, so 24.022. And then the whole entire thing had a mass of this guy, 146.29 grams per mole. And when you multiply that, obviously you have to multiply by 100 because this is just going to give you a decimal. Then what you'll have is 16.45. 16.45% carbon. All right? And then finally, there's only one other element in here, which is oxygen. So you have percent oxygen. Now we did our math here. Our oxygen came out to 95.94. That's what we have that comprises that how much oxygen in that molecule. So 95.94 grams per mole. The whole entire molecule is 146.29 grams per mole, multiplied by 100. So this gives you the decimal. We multiply by 100, and then what we get at the end of the day is 65.69% oxygen. So here we go. Now, if you add all of these up in a calculator, 65.69 plus this, plus this, plus this, you should get 100, or pretty darn close to 100 within a rounding of 100. And that's because we are looking at every single element, the percentage of every element, we add them all together, we should get 100% because we should account for everything. All right? Now, notice, interesting things here. Hydrogen is wrapped up in this polyatomic ion. There's two atoms of hydrogen, so if you were just going to kind of glance at this guy, you might suspect, well, there's only one atom of magnesium, there's two atoms of hydrogen, so hydrogen should be much more of a percentage than magnesium because there's more of it. But in fact, hydrogen only accounts for 1.38% of the whole thing, whereas the magnesium accounts for a whole lot more. Why do you think that is? The reason is right here in front of us, because the magnesium has such a large mass that even though there were fewer atoms of it compared to hydrogen, it totally trumps it because there's double the amount of hydrogen here, but look how teeny tiny the mass of hydrogen is. Hydrogen is the least massive element on the entire periodic table. So even if you have a whole bunch of hydrogen, it's not going to increase the mass of the whole thing too much. So percent mass, part over whole, part over whole. Keep telling yourself that. And obviously to convert to a percentage, you have to multiply by 100. So the next thing we want to do, this is slightly different, but it basically is an exercise in percent composition. So let me write this chemical formula on the board. So it's going to be beryllium 3, aluminum 2, silicon 6, oxygen 18. And what I want to know is what is the maximum mass of beryllium that is possibly obtainable from 1 kilogram of this stuff. So how much beryllium can I get out? So in other words, what I'm saying is there's this chemical formula. It's it's in your lab pantry or something. You pull it out. You measure 1 kilogram of the whole thing. You put it on a bench. So you have a pile of this stuff, 1 kilogram of this giant thing. If you could snap your fingers and pull every single bit of beryllium out of this guy, how much beryllium would you have in grams? How much would you actually have? So this is a great example of when people, they're doing this percent composition and then they read this problem and they're like absolutely lost at first because up until now it's been very mechanical. Okay, find the percent of everything, here's how you do it. You look at something like this and you're like, I have no idea. But you've got to take a deep breath and think logically about what they're asking you to do and know what you can find. What could we find? We could, because we've done it here over here on the board, we could find the mass of the whole entire molecule, and we could find the mass of the beryllium that exists in the molecule. So we could find the percentage by mass of beryllium in this entire molecule. It may turn out to be like 6% or something, or 7% or 8%, whatever it is. But we know we can calculate that because we've been doing it on the board for these other guys. Once we know what the percent by mass is of beryllium, if you know how much of this stuff you have, if you multiply 1 kilogram by whatever percentage you have, percentage of beryllium in the whole, molecule, then what you'll end up with is basically how many kilograms of beryllium exist in there, or how many kilograms you could pull out of this compound if you could snap your fingers and just pull it out of there. So it's sort of a two-step process. Let's go find the percent composition of the beryllium, so we may come up with whatever, 5% or something, and then we're going to just multiply that percentage by how much of this stuff we have. That's going to give us how much beryllium you could feasibly pull out of it, theoretically. So it's a multi-step process. So let's find the mass of the compound. This whole giant compound here. Okay, so what we're going to have is 3 times 9.01, because this comes from the periodic table for beryllium. We have 3 atoms of it, plus 2 for the aluminum. The mass of the aluminum that you'll see is 26.98 grams per mole. 6 atoms of silicon. When you read that off the table, you'll see that each atom of silicon is 28.09. And then for oxygen, we have 18 oxygen atoms, and each oxygen atom is 15.99. Okay, so just to make sure that we're all in the same boat here, this is the beryllium, this is the aluminum, this is the silicon, and this is the oxygen. Right, so let's go ahead and do that multiplication. When we do this multiplication here, we will get 27.03 grams per mole. When we do this guy, it'll be 53.96 grams per mole. When we do this guy, it'll be 168.54 grams per mole. And when we do this multiplication, it'll be 287.82 grams per mole. Okay, so let's add them all together and figure out what we have. We add everything together. 27 plus this, plus this, plus this, we will get 537.35 grams per mole of beryllium 3, aluminum 2, silicon 6, oxygen 18. So I'm going to kind of circle this, but it's not our answer. It's just sort of like an intermediate thing. This is the entire mass of the whole molecule, right? Okay. Now let's find the percent composition of the beryllium. Now in this case, we don't care about the percent composition of aluminum. We don't care about the percent composition of silicon or oxygen, because the problem specifically states, what is the maximum mass of beryllium that we can pull out of this molecule if we had 1 kilogram of this powdery substance, whatever it is. So let's find the percent mass of beryllium. It's going to equal the mass of the beryllium in there divided by the mass of the whole thing. So if we look at our math here, this is how much beryllium we have, by itself wrapped up in this formula. So we have 27.03 grams per mole. We'll divide it by the mass of the whole thing, 537.35 grams per mole. We're going to multiply by 100 to give us a percent. And what we'll have is 5.03% beryllium. So basically 5%. So what this basically means is that however much of the stuff you shovel out of a bucket onto the table, 5% of it, 5.03% of it is going to be beryllium by mass. Right? So now step 2 is applying this number that we've achieved to calculate what we really want to know. If we have 1 kilogram of the substance, of the entire substance, then if we multiply by the percentage of the beryllium in that substance, what we should get back is how much beryllium's in here. Right now, most students, a lot of students would write down 5.03 in here and multiply, right? Because it's 5.03%. But one thing you need to learn in chemistry, and actually any math class, is that you never multiply by percentages like this. You never really, like these percentages are useful for us to understand because it's better to talk about 5% of something than 0.05, which is what you get by this division. But when you actually, and so it's useful, there's a 40% chance of rain, there's a 30% chance of rain, it's useful for discussion. But when you take an answer in a percent and try to multiply it or use it in some other calculation, never, ever, ever, ever use it in terms of this number that you have as a percent. you have to convert it back to a raw decimal. So anytime you have a percent, the way you make it into a raw decimal is you scoot the decimal 2 places to the left, 0.0503. You should convince yourself this is 2 spots to the left, right? You use this number in your calculation, 0.0503. Because this is sort of like the raw decimal. We just multiplied it by 100 to put it in terms of a percentage. But the actual, ratio of beryllium to the total mass is this guy right here. So this is what we really need to use. So we shift the decimal 2 places to the left. That's a rule of thumb that you can use in any math class. If you have a percentage and you're using it in another calculation, convert it to a decimal because you just have to do it. When you do this multiplication, 1 times this is just going to give you 0.0503. The unit is kilograms. So this is kilograms of beryllium that we could possibly extract. So this is the answer, right? So the question was, hey, given this guy, you pull 1 kilogram into a bucket, how much of it could you possibly extract in beryllium? And out of 1 kilogram of this substance, you'd only be able to pull 0.0503 kilograms of beryllium out. Now, if you wanted to convert this to grams, right? If you wanted to convert this to grams, the easiest way to do it, 0.0503 kilograms of something. You could say 1 kilogram is 1,000 grams. So the kilograms cancel, right? And so when you have this guy multiplied by 1,000, what you end up doing is moving the decimal 3 places to the right. So what you will get is 50.3 grams, which is exactly the same thing. So when you say 0.0503 kilograms of beryllium is exactly the same thing as saying 50.3 grams of beryllium. It's just 2 different units, but it's basically exactly the same thing. So I hope this was clear. We've talked about percent composition by mass. We've talked about the definition of what a percent is. We've done a lot in this section. We've talked a lot about percent composition, how to calculate it, what it is. Very important. You're almost guaranteed to have these kinds of questions on your test. Let's go ahead and stop the section here, let you digest it, let you work these problems on your own if you need to. In the next section, we're going to continue along the line of percent composition, but we're going to start to tie in the ideas of the empirical formula and the molecular formulas. It's a little hard to explain exactly where we're going to go with that until we get to some examples, but I promise you it's not hard. As long as you understand this, no problem at all understanding the next section.